All right, welcome back. So likely this is going to be our last lecture of this semester, depending on whether or not we finish the Spark clustering lab today. But so I'll do my best to kind of wrap everything up today. But in case there are some remaining topics, I will try to just upload that on Icon so that you can just watch the video without having to attend the lecture synchronously. Instead, the week after Thanksgiving, I'll just show up in this the same Zoom meeting room, just in case there are questions regarding the homeworks and assignments. Like I said, the project number 3 is due tomorrow, and then there's going to be 2 additional projects. One is for distance and similarity, and then the other is for clustering topic. And then one of them is going to be a bonus project. So like I said last time, for those of you who are concerned that you got some points deducted from the other projects or quizzes, you can use the bonus project to kind of make that up. If you already have a good score, then you don't really have to do the bonus project. So that's kind of the remaining logistics for the remainder of the semester. So with that, last time we talked about k-means clustering, especially in the context of big data. So we saw that the k-means clustering algorithm could be parallelized by considering this gradient descent approach. So the idea was instead of trying to estimate the accurate gradient each time, you could just be sloppy and then take a subsample of the data set, evaluate the gradient only on the subsample, and then use that to approximate the gradient, and then use that to basically try to find the optimal solution. And then the process of finding the gradient is essentially just a summation of the difference between the vectors. And since it is a simple summation, it could be very well parallelized. So that was the kind of the key takeaway message from the previous class. However, there are some issues regarding k-means clustering, especially since k-means is based on this kind of a partitioning using the centroids or the means. When your data set is highly nonlinear, you may end up in a cluster that doesn't really make sense too much. So here are some examples of where k-means clearly fails to cluster a data set properly. So that kind of gives a rise of what is called a density-based clustering. So it's sort of similar to the agglomerative clustering that we saw last time, right? Where we basically group data points together and then merge them to build a cluster, as opposed to kind of a top-down approach that k-means uses. And then in that way, we like to kind of do our best to kind of preserve this underlying structure. So that's what is called a density-based clustering. So I think probably the most popular density-based clustering algorithm is what is called the density-based spatial clustering, aka DBSCAN. So the DBSCAN algorithm, the general idea of DBSCAN is to merge the points based on the density. So what that means is, when you kind of think of this, human cognition process, we have a tendency, this is, like a elementary Gestalt theory in psychology. When we group things together, we tend to group things based on the proximity. So the points that are close to each other, we have, we group them naturally. And then the points that are not, close to each other are not grouped them, instead. And then, we kind of want to separate them as much as possible. So DBSCAN basically uses this idea, okay? So they define this, this algorithm defines this concept of density of a data point. So for a given point, we will evaluate how dense it is with respect to its neighbors. And then based on the density of the point, we will decide if a point needs to be merged into a cluster or not. Okay. So conclusion first, because we're using density-based clustering, it is very, very robust to noise. And then what's really nice about DBSCAN is it's not only robust to noise, but also can actually do a fairly good job in detecting noise. Okay, so when you have a data set that has lots of outliers, the result of DBSCAN can actually provide you a list of outliers that are identified by the DBSCAN algorithm. So the bottom figure over here is actually a good illustration of what I just meant. So as you can see over here, you can find that there's a yellow cluster and then a red cluster and then a blue cluster, and then their shape is fairly, nonlinear. So if we were to use k-means, we probably would not have this, nice clustering result. Plus, there are some, outliers that are denoted in white. Okay. And the white dots are not just for illustration purpose. The white dots are actually detected by the DBSCAN algorithm. So DBSCAN algorithm, when you're given a data set like this, it not only identifies the yellow cluster, red cluster, and the blue cluster, but also identifies the white dots that are, that doesn't belong to any of the cluster. And then that's basically what we define as outliers. So those are, in terms of this density scheme, those are the points that has low density. And then the points with the low density are, at the end of the day, treated as outliers in DBSCAN algorithm. So in order to talk about the DBSCAN algorithm, there are some notions that we have to define. First of all, let's say, we're given a point P in our data set. So, let's say here's a data space, and then we have lots of points. And then one of them, we're going to call him P. And then alongside P, we're going to also consider its neighboring point, let's say Q. Okay. Now, here's the first terminology that we're going to define. So here's the notion of radius. So epsilon is a symbol that we introduced to define the radius of the neighborhood. So when you say neighborhood, okay, how close is your neighbor, and what is the threshold in terms of distance when you define the neighborhood around the point P, right? So what we essentially do is epsilon is a user-defined parameter. So based on that parameter, what we do is to define a circle, okay, of a radius epsilon, and the points that belongs to, okay, that falls within the circle are considered to be the neighbor of the point P. And then points that are outside of this circle are considered, to be non-neighbor. So they're not, taken into consideration when the point P is concerned. So of course, in the two-dimensional space, this is just a circle. But if you go to a higher dimensional space, then it is not circle anymore. So in a three-dimensional world, if your data is distributed in the three-dimensional world, then if you set an object around P that has the distance threshold epsilon, then you're going to see a sphere in a three-dimensional space. So without losing generality, in a random, in an arbitrary dimension D, okay, we can consider a hypersphere. So for a higher dimensional space, there's no way I can visualize this, but you can use your mathematical imagination, right, to expand the concept of circle to sphere to some higher dimensional spherical object. So, still the definition is that we're going to consider points Q, okay, that are in the data set X, that has the distance from P smaller or equal to the radius epsilon, okay? So that's how we define the neighborhood, and epsilon is the user-defined parameter that DBSCAN, asks for. The second, the second user-defined parameter is what is called the min points. Min points literally indicates the minimum number of points in the given neighborhood NP, okay? So we're going to see this later, but min points is basically a parameter that defines if a point is dense enough or not. And then we're going to use this as a threshold to determine if point P is an outlier or a point that belongs to a certain cluster, okay? Now, with that, with those two parameters defined, here we're going to define a few other things. So again, the idea is to cluster data sets, data points based off of the density. So we're going to essentially differentiate low density points and high density points. And like I just said, you know, in order for a point P to be high density point, the epsilon neighborhood of that point P must contain at least the min points. So again, min point is the parameter that we set as a threshold to define if it is a high density point or not. So for example, consider P over here. And then if you set an epsilon sphere around P, then we have 4 points that falls into this, you know, epsilon sphere. And assume that the user defined parameter min point is 4, then that means, you know, we have 4 points in the epsilon sphere, and, you know, P is classified as a high density point, okay? On the contrary, consider a point Q over here that has, again, an epsilon sphere set around it. And in case of Q, we have only 3 points that falls under, falls into this, this epsilon sphere. So with this user constraint, user parameter min points equals to 4, the point Q is considered to be a low density point. And that's basically how we define, you know, what is a high density and what is a low density. Now that we have a definition of low density and high density, here we introduce, you know, 3 very important concepts in the DBSCAN algorithm. So in the DBSCAN algorithm, we classify eventually each data point into 3 different categories. One is a core point, border point, and then outlier points or noise points. So the core point is the points that has high density, okay? So, you know, the points in the data set that has high density with respect to the user parameter epsilon and min point, those are all considered to be core points. So if this is a whole set of points, then if you have a high density, you know, all points that has high density are considered as a core points. And then there are points that are, you know, low in density. And the low density points are further divided into 2 different categories. One is a border point, and then the other is the noise point or outlier points. Border points are the points that has low density, but has a neighbor that is a member of core point. So for example, consider this point over here. So we're still considering, we're considering the min points parameter to be 5, okay? Now, if you consider this red dot over here, okay? I draw an epsilon sphere, and then within this epsilon sphere, I have only 3 points, which means this point is a low density point. However, on its neighborhood, okay? On its neighborhood, there is a point that that belongs to a core point, that is a core point. So for example, well, in fact, this diagram is a little misleading. I think they all kind of needs to be within the same, within the neighborhood. Yeah, it's a little bit misleading. But so then, you know, still this point over here has only 3 neighbors. And then according to this scheme over here, it is a low density point. But if you look at its neighbor, which is this point over here, then this one has, you know, 4 neighbors. So including itself, it has, you know, total 5 points in the neighborhood, in the epsilon neighborhood. And that qualifies as a high density point, okay? So back to this point that we originally started, this point has a neighbor that is a high density point, a core point. And therefore, this point over here is considered to be a border point. On the contrary, consider this point over here. Clearly, it has nothing in the neighborhood. And since it has nothing in the neighborhood, it does not have any neighbor that is a core point, right? So the points that are like this are called the noise points or outlier points. And that's basically how we structure the data set. Now, you know, with this, you kind of, you know, see how where we're getting at, right? Based on some definition of density, okay, we're using the user parameter epsilon and the user parameter min points to define density, right? And then using that, we basically try to define, the core points of a cluster. So the points that are within the boundary of the cluster. And then the border points are basically the points that defines the boundary of a cluster, right? And then, we're going to treat the ones that are ambiguous, okay, as a noise point because they are, far away from the cluster boundaries. So that's basically what's, happening intuitively. Now, since we have to define an algorithm, we have to be more specific than what I just described. We cannot define an algorithm with a hand-waving explanation. So here's some additional concept that we introduced to define DBSCAN. So here's a concept of reachability, more specifically density reachability. So according to the definition, okay, a point Q, okay, is considered to be directly density reachable from a point P if point P is a core point and Q is within the neighborhood of point P, okay? So if you look at this diagram, Q is within the neighborhood of P and P is a core point. So we can say Q is directly density reachable from point P, but the opposite doesn't hold true. So from the perspective of Q, P is not directly reachable from point Q because point Q itself is not a core point. Remember, when we define the direct density reachability, the one condition was that a point has to be a core point. But in case of Q, Q is not a core point, so therefore we cannot say P is directly density reachable from the point Q, since point Q is not a core point, okay? So here's the two takeaways. One is, in order to define the directly density reachable, the points that we're starting from must be a core point. And the second thing is, P being directly reachable from Q doesn't necessarily mean that Q being directly reachable from P. So density reachability is asymmetric, okay? Now we're getting close to the final. So using the density reachability, now we're defining density connectivity. And a pair of point P and Q are considered to be density connected if they are directly reachable as a chain from, basically as a chain from some other point O. So consider an arbitrarily selected point O, and then if point P as well as point Q is directly reachable through multiple chains, okay, no matter how many times the chain is connected, doesn't really matter. But as far as point P is directly reachable from point O, we consider point P and point Q are density connected. Okay, so the very notion of density connectivity is what defines a cluster in DBSCAN algorithm. So simply speaking, in a nutshell, DBSCAN algorithm is an algorithm that finds the groups that are density connected. Okay. So here's clustering criteria. So like I just said, a cluster C is formed, okay, when the points are density connected, okay. So we can actually further break it down to maximality condition and the connectivity condition, but it's basically saying the same thing. So, maximality condition says if P is in a class C, then, and then if Q is density reachable from P, then Q as well should belong to C. But since the notion of density reachable already is involved in the concept of density connectivity, Actually, this one condition kind of describes everything. Okay. So in terms of pseudocode, the DBSCAN algorithm is surprisingly simple. This is, in fact, a pseudocode implementation of the DBSCAN algorithm. It is actually pretty simple. It has just a for loop over here, which traverses all points P in a data set DB. And then what happens over here is we define the density labels. Is it a high density point or is it a low density point? If it is a low density point, it is the noise point or a boundary point. And then from there, here's another for loop that runs within this, which basically says, if point Q, okay, is in if point Q is directly density, if point Q is density connected with the point P, okay, then the point Q should belong to the same class C as the point P, okay. So this is basically, the full implementation of the DBSCAN algorithm. So here is a nice kind of an animation of how the DBSCAN algorithm works. So as you can see, let me try to go back and play this again. As you can see, it kind of propagates from a seed point, and then it merges a point based off of the density. So if this was a starting point for this blue cluster, which is randomly selected, and from this randomly selected point, what happens is you basically, visit a point here and then, try to determine if this point here is density connected with a seed point. And then as far as this point is connected with this point, then, they belong to the same cluster. So the reason why you're seeing this kind of a propagating wave is because we're essentially checking, the points based off of the density connection, okay? So in that way, we can have this kind of a nice clustering result, okay? Where the points that are clustered together, that are, in the space, they are classified correctly as the same clusters. And then the points that are, a little uncertain are, treated as outlier points. So the later part of the algorithm is basically determining the outlier points, okay? And as you can see, the outlier points are not colored in any way. Another thing that you want to pay attention to is the role of the parameters. So on the left-hand side, we have epsilon equals to 1, and then min points equals to 8. So the definition of neighborhood is quite strict, okay? You're setting a circle that is quite large. And then, in this large circle, you have to have this many points within that circle in order to qualify as a core point. Versus on the right-hand side, we have a smaller circle, epsilon equals to 0.6, and with a small number of points, right? So the definition of the neighborhood is, more narrow scoped, right? And the fact that you have a larger circle means that there is a bigger chance that you can merge the points that are, not so close to each other. Whereas under this scheme over here, you better have the points that are very close to each other. Otherwise, they're not going to be considered as neighbors. And if they're not neighbors, then, you're not going to be grouping the points together, right? So as a result of that, the animation is kind of quick, but later in this animation on the right-hand side, you will see like this purple circle and then some other small clusters like that, because we're using a small epsilon to define the neighborhood, okay? So that's one thing that you want to pay attention. The other thing is the DBSCAN algorithm doesn't take the number of cluster K as an input, as you noticed. Epsilon and min points are the only parameters that the DBSCAN is concerned about. Instead, the number of clusters are defined by this propagation algorithm. So as you can see in this animation, it begins with a randomly selected point, and then it propagates, and then wrap up one cluster and then finalize it. and then it visits another randomly selected point from where there's no labels yet. And then it propagates again, like what you're seeing in this animation, and it finalizes the, the grouping of that cluster. It moves to an unvisited point again by randomly selecting an unvisited point, and then do the propagation again, and then again, and then again, so until all the points are visited, okay? So what that means is, DBSCAN algorithm is able to figure out the optimal K for you instead of you defining that, which is a big advantage, because a lot of, big data analytics scenarios, you don't really have a good sense of how many clusters should there be, right? A large data set means, it is really difficult to visualize. Oftentimes they come with a large number of variables. So we're talking about a very high dimensional data space. And having a sense of, how many clusters exist it is impossible, right? So in case of this two-dimensional example, I mean, you can visually recognize those 4 clusters immediately, but when it comes to a high-dimensional space, you don't have that kind of, intuitive, cognition. So the fact that DBSCAN is able to discover the number of K is very attractive, okay? Now, here's one very interesting visualization of those core points, border points, and the outlier points. So original data points are displayed on the left-hand side. And then as a result of running the initial classification of the points, remember at the beginning of the pseudocode, there was a part where we were checking the density. And then as a result of that, we immediately have this kind of a nice classification of the points. So the red dots over here are the ones that are detected to be noise points or outlier points. The green dots, on the other hand, are the points that are detected to be the core points. And then you can see blue dots here and there. And those are the ones that defines the boundary of each of the cluster, okay? Now using this, here's the final clustering result. This is beautiful. Not so many clustering algorithms are able to cluster the points like this, okay? For example, if I was to use a k-means clustering algorithm, probably the clusters would look something like this, which doesn't make sense at all, right? And there are many nonlinear clustering algorithms which tries to set a sophisticated boundary to cluster points that, are so complicated like this. Look at this one, this blue cluster, and then the dark red cluster. I mean, they are, quite heavily intertwined, but as you can see, DBSCAN algorithm can correctly classify them without a problem. So not so many clustering algorithms can do that. So in my personal opinion, DBSCAN is kind of a clear winner for majority of the cases. Almost all the cases, DBSCAN works much better than k-means algorithm. So I personally am a big fan of DBSCAN algorithm, especially because, first of all, it can filter out the noise automatically. And second, it does cluster complicated shapes very well. So in my case, I do research in computer vision and graphics where we have lots of geometric patterns here and there with lots of noise. So the data that I see day to day is pretty much like this situation. You have some geometric pattern going on, and then there are lots of noise, scattered here and there. And I find DBSCAN algorithm works, just beautifully well. But that doesn't mean that the DBSCAN is always desirable. In case when you have varying densities within a cluster, DBSCAN fails. So this is kind of a artificially generated example to illustrate the drawback of DBSCAN. Obviously you probably want to segment this guy over here and this guy over here and this guy over here. And you probably want to differentiate them from this big overarching oval shape. But obviously there's no way that DBSCAN algorithm can differentiate these cases. But as a matter of fact, again, I'm a big fan of DBSCAN, so I might be biased a little bit, but there are not so many clustering algorithms that can actually cluster this kind of scenario. So again, if you were to use k-means, you will probably see something even worse. You'll probably have, the first cluster set over here, and then the second cluster set over here, and then third cluster set over here, which is, totally off of the underlying structure. So it is kind of an artificial example that people created to understand the limitation of DBSCAN algorithm. But I don't know of an algorithm that is able to cluster this kind of situation well. So I guess, to be fair, this is kind of an extreme scenario. However, this is something that you have to keep in mind. So the DBSCAN algorithm does not work well when you set the parameters not so appropriately. So here we have the DBSCAN algorithm applied with a certain combination of epsilon and the min points. And here is a different combination of epsilon and min points. So as you can see, this big circle is nicely classified in the example on the left-hand side. But depending on how you define the neighborhood and the min points, this big circle may end up kind of, scattered into, smaller fragments. So that's kind of, limitation of the DBSCAN algorithm. So the point of this slide is that, don't trust the result of DBSCAN when you apply a kind of a default parameter values that comes with the DBSCAN implementation. So DBSCAN, for example, is available in scikit-learn. Unfortunately, it's not available in Spark. But in scikit-learn, it has a certain epsilon value and the min point value as default. And I've seen a lot of students just submitted a result without actually experimenting with those parameters. And those will clearly generate a result that is not so desirable. Okay. Another thing is, since we're using the density propagation, if you look at this two oval shape on the top, you can see that there's a line in the middle that's connecting the two. So again, your brain probably would like to split them into two clusters, but the DBSCAN algorithm is not capable of recognizing this kind of a thin connection between the clusters. At the bottom, there's another similar scenario. So we have two square-shaped distributions together like this. And then, in the middle, the squares kind of touch each other. And then, it happens to be that no matter how you set the epsilon value and the min point value, there's no way to resolve this connection. So you end up having a cluster that, considers those two squares as the same thing. Or you may end up, in a clustering that looks like this. So we have a bow tie shape in the middle. And then on the side, we have some bunch of fractured segments. And then on the, KC, we have the smallest epsilon value to, scale down the size of the neighborhood so that we can resolve this thin gap between the two squares. So as a result of that, you can see that the colors are different, with respect to this middle point over here. But since we're now resolving the space, with two small neighborhood patches, we end up having lots of kind of a fragmentary pieces, and the segmentation result doesn't look very well. So these are kind of the situations where DBSCAN may fail. But in reality, I mean, what are the chances that your data distribution looks like this, right? So it doesn't happen, a lot. So a lot of time when you have a data set that comes from some sensor measurement or images or whatever, when the data set comes from the real world, there's a very small probabilistic chance where you have this kind of bottleneck feature or a big sphere with a bunch of fragments. Oftentimes, DBSCAN algorithm is going to be just fine to discover the underlying patterns. So that's kind of what you want to know in terms of pros and cons of DBSCAN algorithm. Here's our last kind of comparison. So here we're comparing the k-means algorithm and the DBSCAN algorithm. So in this case, let's say when k goes to 3, the green dots over here are the points that the k-means algorithm is going to converge. Versus in case of DBSCAN, if you set mean points equals to 4, then obviously, these 3 points are going to consider to be outlier points. And then these are going to be clustered well, okay, as far as the distance between the clusters are bigger than the sphere distance epsilon, sphere radius epsilon. So in this case, the DBSCAN algorithm wins over k-means algorithm. Same thing, DBSCAN is especially useful when you have a nonlinear distribution. So you have a distribution like this. When you run a k-means clustering algorithm, then the centers are going to converge to these 2 locations, which ends up giving you, sorry, maybe, I should draw a line like this, and then here's the perpendicular line splitting the 2 centers. And as a result of that, you cannot resolve this, boundary points very well. Whereas if you use the DBSCAN algorithm, for a right epsilon value, it is going to connect all these points over here, and then it's going to connect all these points over here. And as far as the gap between the 2 curves are large enough, it's going to, correctly cluster the 2 segments properly. So those are the situation where DBSCAN clearly wins. Now, here's a situation where k-means might be better than DBSCAN. So here we have 2 clusters visually. However, let's say epsilon happens to be too large, that the distance between the clusters are not sufficiently large enough with respect to the epsilon value. In that case, DBSCAN is going to consider these 2 circles as a whole, one chunk of a cluster, whereas k-means is going to still converge to a right value, which is going to give you a nice split between the 2 chunks. So this is kind of the case where k-means can perform better than the DBSCAN algorithm. So that's kind of an overview of clustering methods in the context of large data sets. And here is a list of algorithms that we didn't cover in this lecture, but could still be useful in clustering problems. So what you need to pay attention to is the scalability table. So obviously, k-means algorithm and the DBSCAN algorithm that I just introduced are fairly scalable, so that it works fairly well with a very large number of samples, and then fairly large number of clusters. Okay, so it works pretty well. The one kind of clause here is when k-means is defined using this mini-batch optimization algorithm, that's when it fulfills this scalability. Otherwise, if you use the naive Loy's algorithm, then k-means is not going to be scalable to a large data set. So those 2 are the method that we just have taken a look into. There are some other methods that are that works fairly well in big data scenarios. For example, in this table, it says Gaussian mixtures is not scalable, but that's not quite accurate. Gaussian mixtures can work fairly well, not with the default version, but when used distributed computing based algorithm. So similar to k-means, by applying some modification, you can have a Gaussian mixture model that can be scaled to a large data set. So in fact, Spark has the Gaussian mixture based clustering algorithm, which you can apply to a large data set. There's also kind of a variant of hierarchical clustering algorithm that is scalable to large samples. But I'm not going to cover everything in this class, because as far as k-means and DBSCAN, then pretty much everything that's relevant when it comes to the clustering of large data sets. So finally, here's kind of a visual comparison in terms of how well these algorithms perform. So in almost all cases, DBSCAN is very stable, okay? Whereas in case of k-means, it clusters the two circles like, in a weird manner. We saw this example in the previous slide. Here also, you can see that the orange cluster is kind of went over to the green cluster. This one, for the defense of k-means, DBSCAN also kind of failed. That's actually the situation that I introduced a couple slides ago, where you have a cluster within a cluster. But if you look at DBSCAN, in almost all cases, DBSCAN works very well with a pretty stable performance. So if you kind of take this table and this sample results into account, you can see that the clear winner for large data set clustering problems is DBSCAN. You should also notice the numbers at the corner, the bottom right corner of each of the figure. So that's the computational time. So again, DBSCAN has, in all cases, it has a few tens of milliseconds. Whereas agglomerative clustering, for example, it can easily go over 10 seconds, which is like 100 times slower than the DBSCAN algorithm. And then if you compare the numbers, actually, you will realize, why I have been emphasizing DBSCAN algorithms, so much in this lecture. So that's all for the theory part. Now, I would like to, oops, sorry. Excuse me. So now I would like to move to Google Colab real quick. Oops. Yeah, I would like to move to Google Colab real quick, and then I'll try to show you, how the clustering algorithms could be implemented in the, excuse me, in Spark. So for that, we're going to need Iris data set from the UC Irvine Machine Learning Repository. So this is the data set that we've used a few lectures ago. I'm going to type that command in the chat so that you can just simply copy and paste. By the way, we have only like 20 minutes, so I'll probably just run through the end of this this code in order to avoid having an additional lecture after the Thanksgiving. But in case you have questions, just feel free to leave that in the chat so that I can answer to them after the class is over. So these two cells, as you know, are the ones to download the data set and then initiate the Spark environment in Colab. And then I'm going to go ahead and create a new session called, why is it gas? I'm going to call a new session called Iris. Okay. And then I'm just going to rush through the, read.csv part, because I believe at this point, you guys all are capable of doing this without too much of explanation. So we're going to read the iris.data file, which is basically the same format as the CSV. And there's no header included in that data file. So this is, how I'm going to read the Irish data set. Actually, I want to see the first 3 lines. Oh, here. So as you can see over here, the column names are not available. So if you want to have the column name, I introduced this function last time, right? As a way to replace the column name with the one that you would like. So the first one is sepal length, and then well, let's break the line. The second column, C1, is sepal width, and then I'm going to just copy and paste because I'll be doing the same thing just multiple times. So the C2 column is petal length, And then finally, the C3 column is petal width. And then the last column is the class name. So this is going to be how I will structure my data set. So now the table looks much easier to understand. Now, one thing so the plan today is we're going to use this iris data set, and then we'll implement a clustering algorithm using PySpark. And then the clustering algorithm is going to take these 4 columns as inputs, and then it's going to cluster the data into k number of clusters, okay? And then we'll see later if the clustering result matches with the class name over here. So for that purpose, okay, before to move on, let's use that string indexer. So this is, again, something that you learned from the previous lecture. So you probably remember this thing called the string indexer. So using string indexer, I'm going to give an index to the class name column. So the input column to the string indexer is going to be class name. And then the output column to the string indexer, let's call it just class index, okay? And then the indexer is an estimator. So the first thing you need to do is to fit your data frame, to fit the indexer to the data frame. And then, you know, the output of an estimator is a transformer, right? So remember that lecture last time, right? So we're going to transform the data frame to have the class index, okay, appended at the end of the table. So let's visualize that. So now you can see that we have additional column added. It's called the class index. So nothing new, right? So we've done this already, and I'm pretty sure you're doing this also for your project number 3. So I'm not worried that you know, anyone is lagging behind. Now, in order to use a clustering algorithm, okay, so the plan, like I said, is to use these 4 parameters to do the clustering. And similar to the linear regression model that we saw last time, you know, we need to convert these 4 columns into a feature vector. And feature vector is basically the, you know, the data format that the Spark clustering algorithm is looking for. So similar to what we did actually for linear regression models, or, you know, other regression models, we're going to convert the 4 columns, we're going to merge the 4 columns into a feature vector. And if you recall, that is where you need to call PySpark ml.feature module import vector assembler. Okay, so vector assembler, we saw this from the earlier supervised learning lecture. You basically define the input columns. So what are the, you know, column names that you want to merge, and then you know, output column is basically where the feature vectors are going to be produced. So for the list of input columns, we in fact need to just you know, add the 4 you know, columns at the beginning. So instead of typing the column names manually, you know, I can probably just select the first 4 columns. So df.columns, if you don't remember, this is how you you know, get the list of the column names, and we're selecting only the first 4 columns, okay, from that. And that's the assembler. An assembler is a transformer. So what I'm going to do next is I'm going to transform my data frame. And then from this, I'm going to produce a new data frame. I'm just going to replace the df data frame. And as a result of running that cell here, you can see that there's a feature vector created. And then the feature vector is basically just a combination of, you know, these 4 columns. So 5.1, 5.1, 3.5, 3.5, 1.4, 1.4, 0.2, 0.2. Okay. So that's basically, you know, how we create feature vector columns. once we have this, this is pretty much it. K-means clustering, okay, is available under PySpark.ml. So we've been keep using the ML library. So that's where, you know, all the regression, you know, algorithms, classification algorithms, and, you know, all the other algorithms are available. So ml.clustering is where you can find the K-means clustering algorithm. So here, let me see if I can pull up the full list of, well, it's not a best way, but K-means with the large K and large M is the name of the module where the K-means clustering algorithm is implemented. And K-means clustering algorithm is, you know, like many other machine learning algorithm, is an estimator, okay? So, you know, basically we're gonna create a K-means model like this. And then since this is an estimator, we need to fit, you know, this K-means algorithm to a data frame. And then the result of that is going to be our, you know, prediction model, okay? Now, for K-means clustering algorithm, there's one parameter that we're concerned about, which is the number of clusters K. So in case of ours data set, we already know that there are 3 clusters. So I'm going to just use K equals to 3. Now, if I run this, nothing is going to show up if everything was successful. There you go. Now, the model, which is the result of fitting an estimator to a data frame, is a transformer that we can use to transform a data frame. So now as a result of this, we can predict labels for each of the rows, okay? And as a result of that, let's just show all 20. As a result of that, you can see that there's some predicted labels produced as a result of K-means clustering. Now, if you look at the class index, they don't necessarily match, okay? But, you know, soon we're gonna visualize to see if the class indices and the prediction results align together, okay? And then you'll realize they do actually align together fairly well. Now, in order to do that visualization, here I'm gonna kind of move out of the Spark, and then I'll use Pandas library instead, because Spark does not have very good functionality for visualization. So here I'm gonna create a Pandas data frame, so PDF, by converting this predicted data table to Pandas, okay? And then let's display the first 5 columns. So now the Spark data frame, this predicted, is converted to a Pandas data frame, and now we have this Pandas table. Now, using this, here's the thing that I wanted to do by converting the Spark data frame into Pandas data frame, because Pandas data frame has, you know, this plot module, which you can use to excuse me, you can use to plot the data set. So I'm going to use a scatter plot where the x-axis is going to be the sepal length. And then for y-axis, let's use petal width. Okay. And then I will like to color the points. The C is the color by using the class index. Okay. So if I run this, then it's going to create a scatter plot like this. One problem is that this is now black and white. So I'm going to probably define a color map. And I think the most primitive color map is the jet. So now you can see that the data distribution looks like this. So the, you know, x-axis is the sepal length, and then the y-axis is the petal length. And then we have the red, green, and blue, you know, based off of the class index. So blue is supposed to be Aries setosa, corresponding to the index 0. And then green, I think, is Aries versicolor. And then the red is Aries virginica, but I'm not 100% sure about that. Now, compare this with the K-means clustering result. So instead of, so we're going to plot the same thing. So the x-axis and the y-axis, is still the same, sepal length versus petal width, but the color is now going to be based on the prediction result. So instead of the class index, I'm going to use the prediction result, but everything else is going to be the same. And now this is the clustering result. Okay, so can you see the difference? So as you know, like I said, k-means is not always optimal. So you should not trust the result of k-means by just running it once. You have to actually run multiple times to get a stable result. So with that, let me actually go back to the k-means clustering code again, try to run it one more time. And I think now it's done with a different random seed. And if I run, actually I don't need to run this again. Well, the result is the same. Interesting. Maybe I should change the random seed. So the random seed, if you are familiar with this concept of pseudo-randomness, the seed is to make it more random. If you don't know what it is, seed is basically, computers cannot generate a truly random number, so it always starts with some seed value. So by giving a specific seed value based off of the current time, you can achieve more random values compared to the default setting. So let's see if that changes the results. I didn't have to run this again, but this one is the prediction. Yeah, there you go. Now this one looks much better. So like I said, k-means clustering, when you use it, you have to be careful because each time you run k-means, the result could be different. So compare this with, I'm going to run this one more time. And I don't know what exactly has been changed, but I recommend you to actually run k-means multiple times and then try to plot them and then compare those plots across each other. You'll probably find a situation where the k-means result is not consistent, okay, across each other. So that's basically how you perform k-means clustering. Although they're not exactly the same, but you can clearly see that some underlying structures could be discovered using k-means clustering algorithm. Okay. Now, before to end, there are a few more things I want to show you. After running k-means, you may probably want to know where the centers are. Okay, and that's could be done simply by just calling model.clusterCenters. And this is going to give you an array of cluster centers. So we have 3 clusters, and each of the centers are represented like this. So you can consider them as the average of the first cluster, average of the second cluster, and then the average of the third cluster. Another useful thing here is the the clustering cost. So if you call compute cost, this is going to give you the a value. Okay, so if you just print it, this is the error function value for the current clustering. So how far the data points are from its center is measured by the coast over here. Okay, so the reason why I'm showing you this is because, well, instead of here, I'm going to show you. So in a lot of cases, you don't have a prior knowledge of K. So in this example, we assume that K is 3 based on a prior knowledge that there are 3 species of iris flowers. But let's assume a generic scenario where we have no idea what the K value is. So in that case, you can actually perform k-means multiple times. Okay, and then evaluate the cost by model.compute cost for a given DF costs. And then at the end, import matplotlib pyplot as plt, plt.plot. So here's a k versus costs curve. And it may take a while because we're doing the k-means clustering 8 times. But after that, it's going to show a plot that shows the optimal number of clusters. So as you can see, the cost is initially very high, and then it decreases, and decreases. Usually, it never increases again, but the reason why it increases is because, like I said, k-means, depending on how you initialize the values, it may converge to suboptimal solutions. So in order to be more rigorous, I actually had to run this k-means.fit multiple times with a different random numbers for each of different k's, and then take the average across them. But anyhow, this is kind of the plot that you're seeing. So what is called an elbow method is one of the methods where you can use to select the optimal number of k. And since the k versus cost plot monotonically decreases, you cannot simply just pick the minimum value, because if you pick the minimum value, then k is going to be the same as the number of data points n, right? That's when the cost is minimized. So what elbow method suggests is you want to find the point where the speed of decrease in this cost curve gets slowed down. So you want to find the phase where the acceleration changes. So that's around 3 and 4. So I would probably call it 4 without being biased from my prior knowledge, which is off of the correct answer, but not too far away from it. So by looking at this plot, you can probably say 4 is the right number for the selection of k. So in elbow method, points like this is basically what you're looking for. Other than the elbow method, there's also a thing called the silhouette method. Silhouette method is available in this thing called a clustering evaluator. So PySpark actually provides silhouette method as a part of their library. So pyspark.ml.evaluation is where you can find this thing called a clustering evaluator. And then internally, what's available is a silhouette method. So this is how you use the clustering evaluator. And the evaluator is it's fairly simple. You just call evaluator.evaluate and then predicted output. So I think that was predicted. And this is going to give you what is called a silhouette value. And the silhouette value ranges between -1 to +1. And as you go closer to the +1, it means the clustering result is good. Small number means essentially the clustering result is not so good. So what you can do is similar to what I've just done with the elbow method. You probably want to plot the silhouette value over the varying k, and then use that curve to determine what is the optimal number of k for your clustering problem. So that's it for today. And like I said, I wanted to finish everything today so that we don't have to meet again after the Thanksgiving. So this is going to be technically the end of the semester. So I would like to thank you very much for being so proactive and doing well in the class. And it's kind of unfortunate that we never had a chance to meet face to face, but I personally really enjoyed the interactions that I had with you. So I appreciate that. And like I said, you still have 2 projects that you have to accomplish, and that's going to be available soon, today or tomorrow. And after Thanksgiving, I will just show up in the same Zoom meeting so that whenever you guys have a question, you can just come in and ask. Okay, so with that, thank you very much again, and looking forward to see you sometime in the future.